So this is our first seminar today. The speaker is Jean-Baptiste Delfau. You should know him by now, because he has been here for 1 year and 5 months. But anyway, yes, we'll tell you that he did his PhD thesis in Paris 7, the University in Paris, on particles with strong range interactions, and then he moved to Tokyo, to Sano Laboratory, to do some mostly experimental work on colloidal Janus particles, the motion of Janus particles. And then he came here, and he has been doing some work related to pattern forming instabilities. I think this will be the topic of this talk.
Thank you, Emilio. So, well, hello everyone. I'm going to tell you about this project I've been doing with Emilio and Cristobal for more than 1 year, basically. And before starting, I also want to mention Hélène Olivier, who was a French master student who came here last year and who also worked with us on this problem. And Bernd Blasius, who is working in Germany. And so as you can see, I'm going to talk about pattern formation. And in particular, I want to show you 2 examples of models in which we have a spontaneous formation of clusters. And we will see that there are some very strong similarities between the behavior of these 2 models, even if they are very different. So, I mentioned clusters, and you know that in general, when you say that you have a system of interacting particles and that you have clusters, the first thing that comes to our mind generally is that you must have some kind of attractive interactions in the system. And actually, I'm going to show you that there are some other mechanisms which are maybe not that intuitive, which can lead to such a formation of clusters. And in particular, I'm going to focus on 2 systems. So the first one here will be a system which is very simple. We are going to consider Brownian particles, which are interacting via central forces, which are purely repulsive. And I'm going to show you that despite the fact that we have only repulsion in the system, it leads to the formation of clusters. And then the second system I want to mention is very different. I'm going to talk about a model of population dynamics. So this time the number of particles is not conserved because the particles can die or other particles can appear in the system. You don't have central forces, but still the originality here is that the burst and death rates of the particles is going to depend on the local density. So the idea is to take into account the effect of competition on the birth and the death of particles. So typically, if you are in a very crowded place, you can expect that the competition is going to be high, so your mortality should increase. And this is what this model does, and we will see that once again, this leads to the formation of clusters. And finally, we will see that in both cases, we can explain this formation of clusters by macroscopic equations, which are very similar in both cases. So my talk will be divided into 2 parts, and I will start with the first part about the Brownian particles I was telling you about. So we are considering Brownian particles, and they are interacting via this kind of interaction potential here. So it's supposed to be soft. We call it soft because, as you can see, there is no divergence in 0. So the particles can overlap. Okay? And so you can see that there are 3 parameters that are important for this potential. The first one is epsilon here, which is the amplitude. R, that gives you the range of interactions of the particles. And then you have this exponent alpha, which is very important because it tells you what is the shape of the interaction potential. So here I have plotted this potential for several values of alpha. And you can see that when alpha increases, the potential becomes more box-like. So you have something which is almost constant at very short distances, and then it decreases sharply. Something I want to say now, and we will see why this is important for the rest of the talk, is that if you have a look at the Fourier transform of these potentials, the Fourier transforms have very different properties. And in particular, when alpha is smaller than 2, this Fourier transform is always positive. So for example, if you have a decaying exponential with alpha equal to 1, you can see that the Fourier transform is always positive here. And you can prove it mathematically. But when this exponent here becomes greater than 2, then you have both positive and negative Fourier components, as you can see here. And we will see that this is very important for the rest of the talk. So finally, we have Brownian particles. We have this interaction potential, so we can write a system of overdamped Langevin equations like this. So you have the interaction here, you have white Gaussian noise in the system, and then
there is no damping.
Here it's overdamped. Yes, so we don't care about the inertia in this system.
There is no damping coefficient.
Because it's overdamped, not underdamped. So we consider that the inertia is equal to 0. So basically, the damping coefficient gamma would divide this potential here with the mass of the particles. So actually this has the dimension of the diffusion coefficient. And so we feed these Langevin equations to a computer and we have a look at how the system evolves. So we start from random positions. And you can see that very quickly the clusters appear in the system. So all the particles gather in some very dense areas. And you can also see that the clusters are distributed in a very regular way. And you have some kind of crystal of cluster with a hexagonal symmetry. Okay. Then there is a phase transition in the system. So this is the steady state that you get if the diffusion coefficient D is very small, or small enough, or if the density, the average density of the system is high enough. Then if I increase sufficiently the value of D, so if I increase the noise in the system, these clusters here would disappear and I would get a steady state which is homogeneous. Okay? Same thing if I decrease the number of particles. Another thing which is important is that we only observe this kind of clusters if the exponent alpha is strictly greater than 2. If alpha is smaller or equal to 2, then you never get these clusters. You always get a steady state which is more or less homogeneous. And finally, a property which is interesting for this crystal of clusters is that if I increase the number of particles in the system, so I take the same parameters as here, and I put some more particles in the system, the distance between two neighboring clusters is not going to change. I'm just going to add more particles in the existing clusters. Okay? So now, in order to understand why we have this phase transition, what we can do is try to derive an equation for the density of the system. Okay? And this was done by Dean and Kawasaki some years ago. And they found that the density of the system rho will evolve according to this equation here. So what you can see is that you have three terms. The first one here is the convolution product between the density rho and the gradient of the potential. So this is the term that contains the interactions in the system. Here, this is the diffusive term, so you have a Laplacian here. And here you have the noise, which has a rather complicated structure. So first you have a gradient before it. It depends on the square root of the density. And also if I write the moment of this force here, this is not a white Gaussian noise. It has a more complicated structure. So now what I can do is non-dimensionalize this equation to see what are the relevant parameters in my system. And if I do this, I obtain this equation here, and you can see that now there are two interesting parameters, two relevant parameters. The first one is this normalized diffusion coefficient, dTl, which is given by this. So basically this is the ratio between D, which is the strength of the diffusion, divided by this product here that tells you what is the strength of the interactions between the particles. And the second parameter which is important is this one here, and this is the relative amplitude of the noise in the system. And you can see that this relative amplitude decreases when ρ0 increases. So actually I'm telling you about the noise, but
What is is Y noise.
Sorry?
You said it was not Y noise, now you put a Y noise.
I said it was not white. No, it's not a white noise here.
It's not the one with the gradient is not white noise.
Yeah, of course.
Exactly.
Exactly. It is.
And
He said that either was not the one.
And talking about the noise, actually we are not going to consider the noise for two reasons. The first one is that, as I told you, when the density is high enough, you can see that the relative amplitude goes to zero. So in principle, if we have dense enough systems, the noise won't be very important. And the second reason, which is the actual reason, is that we have no idea how to deal with such a noise numerically. It's complicated to implement. So we are just going to forget about it. And we keep only the deterministic part of the equation, which is this one here. And so then we integrate it with a pseudo-spectral method, and we let the system evolve, starting from an almost homogeneous state. And so what you can see is that very quickly we recover these clusters because we have zones with very high densities, which are here in red, and zones which are almost empty, which appear here in black. So we recover the phenomenology of the particle simulations. Once again, we only get the steady state if the diffusion coefficient is is low enough, or if the density is high enough. So we recover exactly the same properties we had observed in the particle simulations. So that's the good news, because apparently this equation can describe what happens in the system. And now that we have an equation, we can do a linear stability analysis to try to understand why we have this transition from a homogeneous steady state to these clusters. So we're going to assume that the density is constant and that you have a small perturbation here, which is supposed to be harmonic. And we inject this in the Dean-Kawasaki equation, and this gives us this equation for the growth rate lambda. So the sign of lambda is the important parameter here. If lambda is negative, you can see that this small perturbation here is going to be damped exponentially. So in this case, we are going to come back to the homogeneous state, which is stable. On the other hand, if we have positive growth rates, homogeneous state becomes unstable. And if you look at this equation here, you can see that the sign depends basically on the ratio between these two quantities here, d tilde, and the Fourier transform of the potential. So what it tells us, first, is why we never see the clusters for alpha smaller than 2. Because if you have alpha smaller than 2, as you can see here, V of k is always positive. So this parenthesis here will always be positive, and the growth rates will be always negative, which means the homogeneous state is always stable. On the other hand, if you have a GEM3 potential, for example, then you get negative Fourier components, and you have the possibility to obtain positive growth rates and to destabilize this homogeneous state. And actually, this equation gives us a threshold which means that we can predict what will be the steady state, if it will be homogeneous or clusters. Basically, we get positive growth rates if this parameter here is smaller than minus the minimum value of the Fourier transform. And for example, for the potential we use in the simulations, we can estimate this numerically, and we found this value here. So if d tilde is smaller than this value here, then you will have positive growth rates here, as you can see. But if you increase d tilde sufficiently, at some point, the growth rates become always negative, and so in that case, you recover the homogeneous state. So now, if we want to have a look at the steady state of the Dean-Kawasaki equation, what we can do is just assume that this part here is equal to 0, so we have the two terms here, and we can integrate them rather easily. And if we do, we find that the density in the steady state should be given by this equation here. So now, we're going to assume that the diffusion coefficient is very small. Okay, it tends to 0. So in that case, we can assume that the distribution of the particles is going to be given by a sum of delta functions. Okay, because the clusters, the width of the clusters should decrease sufficiently, and when we are very close to 0, this is a good approximation for the steady state. And then if we inject this in this equation, we can calculate what would be the density in the next order. Okay? And we can iterate this procedure to get an even better approximation. So if we do this work, we find that we can write the density like this. So mu here is a constant, that's a chemical potential. And basically the density is going to depend on this function h of x, which is some kind of effective potential which takes into account all the interactions in the system. And here we have plotted this h of x for two different types of potential. A GEM1 potential, which is in red here, and a GEM3 for a high density and a low diffusion coefficient, which is in blue. And you can see there is a big difference because for the GEM3 potential, this function here has a minimum in 0, while this becomes a maximum for the GEM1 potential. So this tells us why this is a way to understand why these clusters appear, even if we have purely repulsive interactions. If you are considering a given particle, for example, in this cluster, the particle is experiencing forces from the other particles inside the same cluster. So these forces will try to make the particle leave the cluster, and they are here in red. And also the particle experiences the forces created by the particles in the neighboring clusters here in green on this scheme. And so basically whether or not this configuration is stable depends on which is the strongest. If you have strong intra-cluster forces in red, then this force is going to win, the cluster is going to explode, and so this configuration is not stable. And this is what happens here, as you can see, as the potential has a maximum here in 0. In this case, this configuration in cluster wouldn't be stable. So we would come back to the homogeneous steady state. On the other hand, if the extra cluster forces are more important in green, in that case you get a minimum here, so the interactions will act like some kind of confinement force, preventing the particles from leaving the cluster, and then you stabilize this configuration. Okay, so now if we were wondering what would be the properties of these clusters, especially what would be their shape and their widths. So what we do is we just expand this value of h of x that I have plotted in the previous slide. And to the second order, you can show that in good approximation, rho of x should be a Gaussian. So you should have Gaussian clusters. And the widths of the Gaussians should be given by this formula here. So now we have compared this theoretical value to our numerical results with the Dean equation. So here it's in red, and with the particle simulations that are coarse-grained, and this is in blue. And you can see that if detailed is small enough, the agreement is very good. And so this is coherent because to find this theoretical formula, we had to assume that D was very small. And briefly, I want to mention the amplitude equation too. So now we found an expression for rho of x when the diffusion coefficient is very small. And now we can wonder what happens next to the critical point when you have the transition. So we are doing basically the same thing. We assume the density is a constant plus the given perturbation here. And then we expand this perturbation on a very small parameter, xi, here, as well as the diffusion coefficient here. And we inject this in the Dean-Kawasaki equation, and we can find, by doing this, some expressions for rho of x in the vicinity of this critical point here. And I'm not showing you the expressions because they are quite long and horrible, especially in 2D. But what's important here is that if this calculation is true, then the nature of the transition should depend on the dimensionality of the system. So more specifically, if you have a one-dimensional system, the transition should be continuous, while it should be discontinuous in 2D. And so we wanted to check if this was accurate. And so here, well, you have the results in 1D and in 2D. So the symbols you can see here are the numerical results from the Dean-Kawasaki equation and from the particle simulations. And this line here, we cannot see it very well, and here, this is the best approximation we can find using the amplitude equation. So you can see that when we are very close to the critical point, the agreement between the simulations and the calculation is very good. And indeed, the transition appears to be continuous. On the other hand, in 2D, it doesn't work so well, as you can see. So here, these are the numerical results for the Dean-Kawasaki equation. And the straight lines here are the theoretical prediction. So you can see that we systematically underestimate the maximum value of the density here. So it doesn't work so well. But still, the nature of the transition is working because we find that we should have a discontinuous transition, and this is indeed what we see, because clearly there is a theoretical behavior. If you start from a small value here and increase step by step the value of detail, you can see that the transition appears around here. But if you do the other way around, you start here and you decrease the value of detail, the transition happens around here. So you clearly have a theoretical behavior, which is the signature of a discontinuous transition. And I'm just going to finish on this part by mentioning some possible applications. So something that has been known for a couple of years is that if you are considering complex fluids, for example, solutions with polymers of dendrimers, chains of polymers, that kind of things, generally you are going to find clusters in these solutions, in these complex fluids. And some people tried to find what was the effective interaction, for example, between chains of polymers in a solution. And they found that in good approximation, the interaction between the center of mass of these chains of polymers is given by a Gaussian like this. So you can see that this is exactly the same kind of potential we use in our simulations. So now people generally explain the onset of clusters in these solutions by saying that there should be attractive forces at short range between the polymers. But this is not so clear. So here what we are saying is that basically if this exponent is slightly bigger than 2, which could be possible because this is an effective potential, then we could explain the onset of clusters in this solution by these soft interactions that I have shown you in the first part. Okay, so I'm going to stop here for the first part. If you have some questions, maybe you can, yeah.
Well, I have some questions. The first is in the simulation, do you use some cathode?
Sorry?
In the simulation, do you use some cathode?
No, we don't have any cutoff here.
So how you do you use periodic boundary conditions?
We have periodic boundary conditions, and we calculate all the parallel interactions between the boundaries.
But if you don't cut off the potential, how you do? You have to sum over all the period, over all the cells implicating the cells. So how you do that?
Yeah. Okay. Okay. So yeah, true. Yeah. So yeah, indeed there is a cutoff. Yeah.
And
so
if there is a cutoff,
we don't define it, but we calculate the pair interactions between all the particles, considering the boundary conditions.
So you just consider first cells.
Exactly.
And then the thing is, in that case, how do you take into account the reaccelerations, like cutoff macromolecules?
Sorry?
Reaccelerations. I mean, when you cut off a potential, and you use molecular dynamics, you would induce some reaccelerations in the system. So because there is a cutoff, is a sudden drop of the potential, that means in the forces there is a kind of delta. I mean, for the Kawasaki, for the equation I don't have any problem, but for the numerical simulations I don't know to which point what you see is maybe induced for this kind of deltas in the forces.
So I haven't measured what would be the acceleration in the system, to be honest, because I assumed that because the potential is very steep, basically the cutoff wouldn't change anything.
Is the steep depending on the noise? I mean, because this saturates to 1. So what's the temperature in this system? You assume 1, no? Something like that.
So if you want, well, this is an overdown system. So I'm not sure you can define properly temperature because you don't really have a mass.
The problem, this is an overdamped system, so there will be no acceleration because acceleration is always zero. And then you can have the potential is slightly changed, but it's always the range of the potential is always R, which is much smaller than the system size. So I don't expect this is makes a problem. We make a problem for long range interactions, of course, because we know better than.
Okay.
But in the case of in an overdamped system, the diffusion is a measure of temperature, it's proportional to temperature. It's diffusion divided by temperature. Diffusion is temperature divided by the damping constant.
Yeah.
So the homogeneous state is always there, but sometimes unstable. Are there other unstable solutions maybe coexisting?
In the 2D case, you have two solutions close to the threshold, the cluster solution and the homogeneous state. Sorry?
Okay.
In the other cases, I don't think so. I think the homogeneous would be the only one.
What do you think? What do you think is the difference, the regional difference between simulation and theoretical results in 2D for the instability?
Okay, so in 2D, what we observed is that the agreement between the particle simulations and we have no noise, and we have seen that the relative amplitude of the noise should decrease when you increase the density in the system. And indeed, when we compare the position of the threshold, so when you have the transition in 2D, we can see that we get closer to the theoretical value when we have more particles in the system from the particle simulation.
Yeah, I have a question. Here you say that for alpha greater or equal than 3, you have negative components in your Fourier transform.
Alpha greater than 2.
Oh, because like in this slide it says 3. So that was confusing. That was my question. Here you're saying 3.
Oh yeah, sorry. No, this
okay,
is
this is
a
okay.
mistake.
Then I have no.
Sorry. Sorry.
That's fine.
Okay. If there is no more question, I'm going to go to the second part, which should be shorter. And here this is another model which is very different. We are going to consider this model of population dynamics I told you about in the introduction. So this time I'm considering Brownian particles again, but there is no interaction potential. But instead, the value of the birth and death rate of each particle is going to depend on how many particles are around it, basically. So you can see that if I take into account, if I take for an example di, which is the death rate of a particle, the death rate is given by a constant, d0, and then you have, it is modified by this n of r parameter. And n of r is simply the number of particles in this disk of radius r around the position of the particle, minus 1, because we don't count the particle we are considering. So here the idea is, once again, that if you are in a very crowded place, then the competition, for example, for food should increase, and so your mortality rate should also increase. So then we simulate this kind of system, starting once again from random positions. And here is what we observe if we wait a little bit. So you can see that very quickly the particles gather in some very dense areas. And on the other hand, you have like empty zones around them. And we recover a steady state which looks very similar to what we had in the first model. We still have crystals of clusters, which are hexagonal. We only observe them if the diffusion coefficient is low enough. So once again, we have a phase transition from something homogeneous to a state with clusters like this. And here it will depend, instead of depending on the density, it depends on this parameter here, V0 minus V0, which we are going to call the growth rate, because this is the difference between the constant part of the birth rate and the death rate here. Okay? So once again, we can derive a macroscopic equation to describe the evolution of this system. And here it is. And once again, we are going to forget about the noise, which is a bit complicated too. So we just keep the deterministic part, and we can rewrite it easily in this form here. And so here you can see the structure of this equation is very close to what we had before. We have a diffusive term once again, and also a convolution product between rho and this kernel function g that contains all the interactions between all the information on the interactions of the particles. So you have the constant b0, d0, etc. And if we integrate numerically this deterministic part, starting from random conditions, once again, after some time, we recover some kind of crystal of clusters. So we recover the same phenomenology we had before. You can note that here the cluster is not perfect, you have some defects, and we will need to wait a long time for them to disappear. So once again, we can do exactly the same kind of work we've done before. So we do a linear stability analysis, assuming that we have a homogeneous state plus a perturbation. We inject this in the new equation we found. And once again, we get an equation for the growth rate of the system. And you can see that basically we have the same problem as before. Everything depends on this value here, which is the Fourier transform of the kernel function that contains the interaction. If this thing is always positive, then once again you always get a negative growth rate, so the system will always be homogeneous in the steady state. On the other hand, if you have negative components, then if you have a low enough diffusion coefficient, for example, you will get some positive growth rates that you cannot see here, but which are supposed to be in yellow. And so once again, we switch to the cluster steady state. And very briefly, now the clustering mechanism is a bit different in that case. So imagine that you are in this configuration. So once again, you have clusters. If you are a particle in this cluster, you are going to feel the influence of all the particles in the same cluster, right? And this is going to modify your birth and death rates. Same for this one. But if you are in between here, then this is a highly competitive zone because you are going to feel the influence of both the clusters, which means your mortality rate is going to increase a lot and your birth rate decrease a lot. So there, if you wait some time, these zones here are going to be depleted because of this strong competition. And to finish, I want to show you briefly two examples where the competition can lead to this kind of clustering. So the first example you can see here is a photo that was taken in Niger. And yeah, maybe you can see that here what's supposed to be green are trees, okay? And on the other hand, what's brown are areas where you have basically no vegetation at all, or very few. And if you look here, you clearly have some clusters where you have many trees, and in between you have absolutely nothing. So here in that case, the reason why we have this is because when you have a tree, the roots of the trees are going to expand, and they are going to catch the nutrients in the ground, okay? And this leads to a local concentration of the nutrients in the areas around the trees here. So if you are next to the existing trees, you have a positive feedback because they are bringing back all the nutrients, okay? But on the other hand, if you are in this empty area here, you have no nutrient at all, so you have nothing to eat and you die very quickly. So here, in this case, the competition is due to the concentration, the accumulation of nutrients by the trees.
What is the scale of the picture?
I forgot to put it. I couldn't tell you. I don't remember.
No,
I think it's tens of meters, something like that.
that,
Tens of meters, I think.
Tens of,
so the
something
distance
like
between two spots is
No, 20 is tens of meters. I think it's the.
Each cluster is a few trees.
yeah. And so the second example here is a picture that was taken in the US. And if you look closely, you can see that some spots, like here or here, are green, while the others appear gray. So here the idea is that these are tussocks, so some kind of big grass that grows vertically, and when it dies, it falls radially like this. And here the mechanism of competition is that when a tussock falls, sometimes it falls on a young tussock, which doesn't have access to light anymore. Okay? So because the young tussocks in these gray areas here have no access to light, they cannot grow. And this is why you have this cluster-like distribution here. So now here the competition is through the light availability in the system. And I'm going to finish here. Just as a conclusion, we have seen two models with hexagonal clustering. We have seen that we can explain this clustering in both cases by deriving macroscopic equations. And also we have seen that the linear stability analysis shows that the patterns come from this instability of the homogeneous states. And just before finishing, I want to mention something. So we were wondering if we could find a system of animals in which we could observe such kind of clustering. And so what you see here is a coyembola, I think, or springtail, which is some kind of small arthropods. So it looks like an insect, but technically it's not an insect. So if you're a biologist, you should say it's an arthropod. And here you have a pool of water on the ground, here on the campus, when it had rained. And you can see that the black dots that you can see are these guys here. And basically they don't like water. So when it rains, they are trained to come together and they form clusters. So if you've been working for more than a year on these topics like I do, you want to see hexagonal clusters here. So I don't know if this is really hexagonal, maybe not. I have to be honest. But I think it would be interesting to study the clustering mechanism in this system. And with this, I'm going to thank you for your attention.
To prove the homogeneous is unstable, then you put that it goes to like hexagonal pattern, or you compute the wavelength of the why hexagonal?
You mean what selects the wavelengths of the patterns?
And why hexagonals? You have to compare the direction.
Why hexagonals?
I mean, does it come out of the linear stability analysis?
No. The hexagonal shape is given to you by the amplitude equation. The linear stability analysis doesn't tell you anything about the geometry. It can tell you what will be the typical lengths between two neighboring clusters. But if you want to know the geometry, you have to compute the amplitude equation.
Did you do it?
Yes, we did. And indeed, it gives you the hexagonal symmetry in 2D.
But I think if one wants to be more honest than this, you assume this hexagonal and then you compute. But different analysis of the equation should tell you that it's hexagonal and not other thing. But we have
What is
done
called
that.
the
So it's in the
Wiggin-
equations, and there are techniques to extract this, but we haven't.
The Wiggin method analysis should tell you that. No,
It's too complicated.
output.
But we demonstrate that there are hexagonal solutions. That's
Stable.
and stable.
In the second model, you take a potential which is a constant. For a given radius, it's constant, and then
Well, we don't really have, strictly speaking, but yeah, it's a constant. Yeah.
and this is what gives you then this Bessel function of KR.
Exactly. Yeah. This G of K. Where is it? Here. This G of K here is we can express it according to a Bessel function.
And another question, you have another parameter which is called alpha. No? It's the ratio between the birth and death related to the distance.
Yeah.
How does this affect the result?
Yeah, this one here.
How you moved it?
I have no idea. I don't know if you already moved it. In my simulations, I kept it constant, so I didn't have a look at the influence of this parameter. I don't know if in the previous studies. Sorry?
Alpha was 0.
Yeah, in the first picture, it was 0.
Yeah,
That means
it's equal to 0.
there is no variation of the depth.
Exactly. I don't remember if you did something about changing alpha. I didn't.
The level, the mean density depends on alpha. The mean density. I don't know what else. What is the mean density depends on alpha.
Yes.
Well, another question is a comment about the columbola on this pitch. Have you heard about that? That is not whether it is hexagonal or not. Or for what matters, the previous one also, it is not clear whether it's hexagonal or not. I would say that when you have such a system and it becomes so you know this comes from a Turing instability, a pattern forming instability type. No? So you get homogeneous becomes unstable, and then you get a function of that. Your simulation of course, that is a small system which is ideal, so you have few modes competing. No? But in a large system, and noise, what you have may have several sets of different hexagonal patterns that at instability become together. So this may be very long transients, or even frozen states which are not really open. So
you mean you get some defects in your pre-slope?
So these are many sets of hexagonal, so many sets of 6 which are coexisting, probably non-linear competing. But this maybe last for a few hours, maybe it should take days to get to more of the thing. So in that sense, I would say it is a hexagonal structure. It could be squares as well, but
you're saying
you'll never know.
It's transient.
I say so, or it's a quasi-transient or something.
Maybe.
So you can know.
We're still not very sure about the kind of interaction between the negative attractive. So in that case, I guess if you wait for one, you get one big cluster in the center.
In geography, people like to see hexagonal structures between cities. Like it is a very classical book, theory of the central place theory. And I never read the paper, but there's a paper that basically says if you distribute randomly points and hierarchy in the dimension of the cities, you get hexagonal structure without any reason. Just is the way randomness goes. Cannot be just that this is a random distribution of sizes and points in XY?
But I guess you need, well, I don't know, I'm not an expert in geography, but you need some kind.
We have someone who is officially geographer.
You need some kind of interaction to get this hexagonal structure, right?
That is what the geographer think, but it's not what the paper by a mathematician or a physicist says.
Okay.
The mathematician or the physicist, I don't remember who, but they never read the paper, but they gave me and told me about it. Is you just take random points, you give random ranks, and you will find the thing that the geographer would like to see.
Well, the only thing I could say is that indeed in 2D these hexagonal structures are not very rare. You can find them in several systems. Now, is it something you will automatically get? I don't know. I'm not sure we can say that. I guess you need some particular kind of interaction.
One property of hexagonal pattern is that the close packing into dimensions. Because you can arrange clusters the closest as possible is the hexagonal. So there is some kind of repulsion. You expect this to be found because it's the way to be as far as possible without touching. That's one property that may explain why it appears many times. But I don't know if cities sometimes touch and coalesce. I don't know if this is a good explanation for cities.
Other questions?
No? Okay. Then, no, thank you.
hexagonal, and you see they continue to match. So if you put the homogeneous distribution and then they try to pack together, so this may end up with P.